Hey guys, welcome back to another RASK Maths tutorial, and in this video I'm going to be showing you guys how we can derive the 2x2 rotation matrix. So if you don't know, the 2x2 rotation matrix is essentially just a matrix which allows you to rotate points in a 2D plane by a specified angle. And it basically looks like this. So it's cos theta sine theta minus sine theta cos theta. And I'm going to be showing you guys how we can actually derive this using just using basic matrices skills. So for example, before I derive it, let's just show you guys an example. Theta is actually anti-clockwise, so where theta is the angle rotated anti-clockwise. So let's just take r when it's 90 degrees. Well, that's going to be cos of 90, which is 0, sine of 90, 1, minus sine of 90, minus 1, and cos of 90, which is 0. So here's our 90-degree rotation matrix. And let's see what this actually does. So let's say I wanted to rotate the point. Let's say this is 2, 1, and I wanted to rotate it 90 degrees anti-clockwise, so it ends up somewhere over here. We know that this is going to have to be minus 1, 2, like so. I'll just draw in some lines so you can see that. So to rotate a point, it's pretty simple. We just have to multiply the transformation, which in our case is going to be this matrix we just worked out, multiply it by the point in vector form. So we could just do something like 2, 1. And now if we multiply these matrices, remember row by column, so multiply this row by this column, we get 0 plus 2 minus 1 minus. So that's going to be minus 1, and then the bottom one we get 1 times 2 plus 0 times 1, which is just 2. And you can see that's given us our final point over here. So you can see this rotation matrix definitely works, but I think that's pretty obvious. It's been used for ages. And how we can derive it is, well, you need to understand how rotation matrices work in the first place, or how matrices work in the first place. So if we have a bunch of points, let's just have an initial point of 1, 1, and we've multiplied this by a random matrix. Well, what this is going to be is this 1, 1 point is essentially just going to get transformed by the matrix such that, well, okay, I think it's easier to show it on a point on the axes, or it's easier to show this on the identity. So this is basically our unit square. We call this vector I hat, and we call this vector j hat to represent the x and y axes. And this is going to be I hat and j hat like so. So this is point 1, this is point 2. Doesn't actually matter how we represent them because we could separate these out. But essentially, when we multiply this by a matrix M, then let's just say M is defined to be A, B, C, D. I hat is going to get moved to AC, so it's going to get moved somewhere over here, where this point is AC, and I'll call this I hat dash. And J hat is going to get moved to BD. And if assuming all these points are positive, then BD is just going to be somewhere over here. So that's basically how our matrix transformations work. We transform this unit square by these sort of points, and then everything in between is just interpolated. So if we had a point here, well, parallelism, I don't know if that's a word, but it gets maintained. So if lines are parallel before, they're going to be parallel afterwards. So these two lines are still going to be parallel, and these two lines are still going to be parallel. And so this point would get put over there, like so. And yeah, that's basically how matrix transformations work. So if we want a rotation, well, we have our two unit vectors, I hat and j hat. And if we want to rotate them like 90 degrees anti-clockwise, well, our I hat's going to become over here, j hat is going to be over here. So we can see our final rotation matrix if AC is a point where I hat goes, AC is going to have to be 0, 1. And BD is the point where J hat goes, and this is clearly at -1, 0. So you can see that's our 90-degree anticlockwise rotation, which we also worked out over here. And how can we work this out for a generic rotation? Well, okay, let's take a look at a slightly larger example. So this is our initial I hat, this is our initial J hat, and let's rotate it by some random angle. So this is I hat dash, where that is the angle we've rotated it by, and rotation maintains that these two are at right angles, so J hat is just going to be somewhere over there, where this as is also the angle we've rotated by, and that's an angle. So to find our A, B, C, and D, we just have to look at the x and y coordinates of I hat and J hat, and you can see this is just going to be, assuming these are of length 1, which they are since they're unit vectors, this length here is simply just going to be cos of theta, right? Because this is of length 1, so we have cos of theta equals adjacent over hypotenuse, or I hat dash x coordinate over 1, so therefore I hat dash is just going to be equal to cos theta like that, the x component of it. And similarly, we can work out that this height here is going to be sine of theta, because sine of theta is equal to opposite this over 1, so therefore the opposite is just equal to sine of theta, like so. Doing a similar technique on J hat, we need to be a bit more careful of science, because notice how this is similar to the sine theta over here, except it's pointing in this direction, which means it's now negative sine theta. And this height here, well, this is cos of theta, because it's essentially just this flipped on its side. So putting all this together, we can see the m of theta, well, A and C are just corresponding to cos of theta and sine of theta, because A is the x coordinate and C is the y coordinate. And similarly for J hat, we have the x coordinate B is minus sine of theta, and the y coordinate D is cos of theta, like so. So that's nice and easy. We've just managed to derive this rotation. So we've proved it only works for small angles, I mean going up to here, but this actually translates nicely into all other angles, like all the way 90 degrees, 180 degrees, 360 degrees, everything in between. And that's just because these are essentially just points on the unit circle, which we've added our sines to. And always remember, J hat is essentially just I hat, but 90 degrees rotated anti-clockwise. So that's how we get negative x there, and then the x coordinate becomes the y coordinate, just like that. So yeah, that's how we derive this rotation matrix, 2x2 rotation matrix. And using this 2x2 rotation matrix, we can actually make any rotation matrix. We can make a 3x3 by just multiplying these together in separate axes, but that's slightly complicated, so maybe that's for another video. But yeah, that's how we derive the 2x2 rotation matrix. Thanks for watching, and I'll see you guys in a future tutorial. Bye.